Schrödinger's cat. It's one of those phrases, isn't it? You hear it everywhere, kind of hinting at something really weird, maybe wonderful about reality. This whole idea, this thought experiment, picturing a cat that's somehow both alive and dead. It's really like clawed its way out of quantum physics.
It absolutely has. Leapt right out of the technical journals and into, well, popular culture.
So today on the deep dive, that's what we're digging into. The story behind this famous paradox, why it still gets people talking, thinking almost 100 years later.
Exactly. And our, let's say, mission here is to figure out how such a deeply technical argument, something really born from quantum mechanics, became this go-to way of exploring reality, our understanding of it.
Yeah, and it's not just physics, is it? It touches philosophy, how we know things.
Even literature, as we'll see. And we're drawing heavily on a great essay from Aeon to guide us through this.
Okay, so let's jump in. 1935. That's when the cat makes its first appearance, right? Thanks to Erwin Schrödinger.
That's right, the Austrian physicist. But it wasn't like a standalone paper titled My Cat Paradox.
No.
No, it actually appeared inside this really long, dense review he wrote. He was looking at the present situation, his words in quantum mechanics. And, well, he wasn't entirely happy with it.
Ah, so he was critical.
Very much so. The review is full of technical stuff, maths, really complex arguments, the kind of thing usually hidden away in university libraries.
Okay.
But then buried in there is this one short paragraph, almost mischievous, you could say.
Yeah.
And he lays out this thought experiment that, well, here we are still talking about it.
So the key thing is he used this kind of crazy scenario to make physicists face up to something.
Precisely. To face the, frankly, bizarre implications of taking quantum theory literally and applying it to the world we actually experience, the macroscopic world.
Okay, so tell us about the setup. It sounds pretty grim.
It is quite unsettling. He imagined a steel chamber, completely sealed off. Inside you have the cat, and then what he called a diabolical device.
Diabolical, right. What did that involve?
Okay, so you got a Geiger counter. Next to it, a tiny, tiny speck of radioactive material. So small that in 1 hour, there's exactly a 50-50 chance that one atom will decay.
50-50, okay.
If an atom does decay, the Geiger counter detects it and triggers a mechanism. This mechanism releases a hammer.
Oh, boy.
Which then smashes the small flask of hydrocyanic acid, poison gas.
And the cat?
And the cat dies. But crucially, the cat can't interfere with any of this.
Yeah.
It's just there.
Right. So after 1 hour, 2 possibilities. If no atom decays.
Counter stays silent, hammer doesn't fall, flask is intact, cat's fine, alive.
But if an atom does decay?
Click goes the counter, down comes the hammer, smash goes the flask, and yeah, the cat dies.
Okay, simple enough outcomes, but here's the quantum twist, right?
Here's the quantum twist. According to quantum theory, as it was understood then, after that hour, the radioactive atom itself isn't definitely decayed or definitely undecayed. It's in a superposition of states. It's sort of both.
Yeah.
Think of it like a blurry photo that hasn't resolved yet. Both possibilities exist simultaneously in the quantum description, the wave function.
Right, that inherent fuzziness of the quantum world.
Exactly. And here's the core of the paradox. If the atom is in this fuzzy both states at once condition, then its fate is tied, or entangled, that was Schrödinger's word for it, with the whole device. The counter, the hammer, the poison.
And therefore the cat.
And therefore the cat. The quantum wave function for the entire system, including the cat, ends up describing a cat that is simultaneously living and dead.
Wow.
Schrödinger's own phrase was mixed or smeared out in equal parts, living and dead.
That just sounds impossible. Completely counterintuitive, a living and dead cat.
Absolutely. It feels like something out of science fiction, not physics.
And that was his point.
That was precisely his point. He explicitly called it a ridiculous case. He wanted to show that applying the standard interpretation of quantum mechanics directly to large-scale objects, things we see and interact with, leads to conclusions that seem absurd.
So it wasn't that he believed a cat could really be alive and dead.
Quite the opposite. He was using it to say, look, there must be something incomplete or misinterpreted about this theory if it leads here.
Okay. And it highlights this problem. You called it wave function collapse.
Yes, exactly. Quantum mechanics is great at describing these superpositions, these possibilities, but it doesn't clearly explain how, when we make an observation, lift the lid, as Schrödinger put it, this fuzzy state suddenly resolves into one definite outcome.
A live cat or a dead cat, not both.
Right. How does the or happen? The theory described the and state before observation, but the transition to a definite or state upon measurement. That was the mystery. That was the measurement problem.
So the paradox really nails that tension, doesn't it? between the quantum probabilities and the definite reality we, actually experience day to day.
Perfectly. It forces you to ask, is the cat really in that state?
Yeah.
Both alive and dead. It just feels wrong.
Yeah, like you said earlier, we don't think of a spinning coin as being both heads and tails in the same way, right? Even if we don't know the outcome yet, what's the difference?
That's a really good point, and the Aeon essay brings this out. With the coin, we intuitively believe the head side and the tail side exist, they're definite, even while it's spinning. Our ignorance doesn't change the coin itself.
Right.
But quantum mechanics suggests something deeper. At the subatomic level, reality itself might be probabilistic until measured. There's a lot of experimental evidence, actually, showing that assuming particles like electrons have definite properties before we measure them leads to contradictions.
So we can't just dismiss the superposition idea easily.
Not at the quantum level, no. The evidence points towards that inherent probability.
And Schrödinger wasn't alone in feeling uneasy about all this, was he? Einstein comes to mind.
Absolutely. Albert Einstein famously disliked the probabilistic nature of quantum mechanics. His famous quote, "God does not play dice."
Right.
And earlier in that same year, 1935, Einstein, with Podolsky and Rosen, the EPR paper, argued that quantum mechanics couldn't be a complete description of reality. They felt something fundamental was missing.
So they shared Schrödinger's concerns.
They did. While their specific arguments in the EPR paper were different, they shared this deep unease. And apparently, their correspondence that summer directly spurred Schrödinger on to develop the cat paradox. It was like the ultimate stark illustration of their shared discomfort.
Okay, so the cat is born from this high-level physics debate, but then it kind of went quiet for a bit.
For a while, yes. It remained mostly within academic circles, this provocative paragraph in a long review. But then it resurfaced more publicly in 1957.
How did that happen?
At a conference in Bristol, in England, the American physicist David Bohm brought it up again.
Did he use the same setup? Geiger counter and poison.
He tweaked it slightly, which is interesting. He used the example of a single photon hitting a half-silvered mirror.
Okay, so the photon might pass through or it might bounce off. 50-50 chance again.
Exactly, 50-50. And if it passes through, in Bohm's version, it triggers a mechanism to kill the cat. He actually suggested a gun in his scenario.
A gun. Even more dramatic. But the principle's the same.
The principle is identical. Link a macroscopic outcome, the cat's life or death, directly to a fundamental quantum probability.
And it kept evolving. I think you mentioned a philosopher got involved, too.
Yes, in 1965, Hilary Putnam. He wrote an essay also using a similar setup photon, mirror, and gear. But this time the mechanism involved electrocution.
Keeping it cheerful.
Yes. But his conclusion was quite pointed. He basically said that even then, no satisfactory interpretation of quantum mechanics exists today. The paradox was still highlighting these really fundamental conceptual problems.
But then the cat escapes the lab, escapes the philosophy seminar, and leaps into, well, everywhere else. How did that happen?
It seems a key moment involved the science fiction author Ursula K.
Oh, interesting.
Yeah, in 1972, she was apparently researching Einstein and just stumbled across a mention of Schrödinger's cat. And she said she was just completely entranced by it, by the implications.
I could see why.
And just 2 years later, 1974, she published a short story, the title, simply Schrödinger's Cat.
And did she use the original setup?
Interestingly, no. She used Bohm's version.
Huh.
The photon, the mirror, the gun.
Huh.
And there's this great bit of dialogue in the story between the narrator and a dog named Rover, of all things. They're talking about the photon, how you can't predict it. And Rover says, if you want certainty, you must create it yourself. How? By lifting the lid of the box.
Wow. That really captures it, doesn't it? The role of observation.
It really does.
Yeah.
And that story seems to have been a major turning point, a catalyst.
So after Le Guin's story,
the cat just exploded into popular culture. Seriously, it started appearing all over the place. Other sci-fi, mainstream books, films, TV shows, you name it. And also popular science books, like John Gribben's In Search of Schrödinger's Cat, which brought the idea to a huge audience.
So a compelling story like Le Guin's can take this really complex scientific idea and just make its philosophical side accessible.
Exactly. It translates the weirdness and the deep questions into a form people can connect with.
It is pretty amazing how this abstract physics thing could grab hold of the public imagination like that. The Aeon essay suggests it's those what-if questions it raises.
I think that's right. It forces you to think about choices, about chance, about what reality even is. It's like you said, a kind of quantum butterfly effect almost. A tiny uncertainty blows up.
Yeah, the essay mentions sliding doors moments, like the movie.
Exactly like that. Missing a train or catching it, and your life splits onto totally different paths. The cat's fate hanging on that single atomic decay. It mirrors that feeling that huge consequences can hinge on these tiny, unknowable moments.
And Le Guin, she really pushed the philosophical side too, didn't she? Questioning why looking, observing, forces a result.
She did. And she asked that really profound question.
Sure.
What if the observer, what if we, are also part of a bigger entangled system? If we are, she asked, who is doing the looking?
Whoa, that gets very deep very quickly, thinking about consciousness, its role.
It really does. And that line of thought connects quite naturally to one of the most, well, mind-bending interpretations of quantum mechanics out there.
Which is?
The many worlds interpretation, proposed by Hugh Everett III, actually back in 1957, the same year Bohm brought the cat back up.
Many worlds. Okay, what does that entail? Does the wave function still collapse?
No, that's the radical part. Everett said the wave function never collapses. Instead of the superposition resolving into one outcome when you observe it,
Yes.
the entire universe splits into parallel branches,
Yeah.
one for each possible outcome.
Splits, you mean literally creates new universes.
That's the idea. So for the cat, when you open the box, the universe doesn't just pick alive or dead, it blanches. In one universe, you open the box and see a live cat. In another, completely separate universe, you open the box and see a dead cat.
What about me, the observer?
You split too. You become entangled with the outcome. There's a version of you in the live cat universe and a version of you in the dead cat universe.
Okay, that's a lot to take in. So why don't we feel ourselves splitting or sense these other versions?
Well, the interpretation says that as soon as the split happens, these universes diverge. They become completely separate realities. There's no communication, no awareness between them.
Yeah.
So you wouldn't have that eerie sensation of coexisting with your other selves, as the essay puts it.
Right, but the implication is staggering. Every quantum event, every choice maybe, constantly splitting reality.
That's the implication. Countless parallel universes, branching constantly. It takes those what-if scenarios to a whole new level. Think about all the different choices you could have made. Many worlds suggests maybe all those possibilities are playing out somewhere.
The essay mentioned novel dark matter.
Yes, by Blake Crouch. It explores exactly these kinds of ideas, versions of oneself living vastly different lives in parallel realities. It's a fascinating fictional take on it.
It's incredibly provocative, the many worlds idea, but it's important to stress this isn't necessarily how most physicists view the situation, right?
Yeah, that is a really crucial distinction, yes. While many worlds and the sheer weirdness of superposition capture the imagination, most working physicists tend to stick to more, let's say, pragmatic interpretations.
Like the Copenhagen interpretation.
Primarily, yes. That's the interpretation developed back in the 20s and 30s by people like Niels Bohr and Werner Heisenberg. It's often considered the sort of standard view, though even that has nuances.
And Copenhagen says.
Essentially, it treats the quantum wave function less as a literal picture of reality and more as a tool, a calculation device, as the essay notes. It's a mathematical framework that lets us calculate the probabilities of different outcomes when we perform an experiment.
So the superposition isn't a real state of being both things at once.
In the Copenhagen view, it's more a reflection of our knowledge. It represents the probabilities before we measure. When we talk about the cat being alive and dead, it means the wave function assigns probabilities to both outcomes, and we don't know which one we'll get until we look. The reality is what we measure.
It's about prediction, not description of some underlying cat state.
Largely, yes. It tells us the odds. The focus is on what we can observe and measure, rather than speculating too much about what might be really happening unobserved.
Okay, and what about this Heisenberg cut the essay mentions, this boundary between quantum and classical?
Ah, yes. The Heisenberg cut is this idea that, for practical purposes, we have to draw a line somewhere. On one side, you have the quantum system behaving according to quantum rules, superposition, probability waves. On the other side, you have our measuring device, the observer, the cat itself perhaps, behaving according to classical rules, definite states.
Where do you draw that line?
That's the tricky part. Heisenberg thought it didn't really matter precisely where you put it for the calculations. Bohr had ideas about it being at the point of some irreversible active amplification, like the Geiger counterclicking, a macroscopic event triggered by a quantum one.
But the general idea is?
The general idea among physicists is that whatever quantum weirdness is happening, it resolves itself. The wave function effectively collapses long before you get to the scale of something as large and complex as a cat. The cut happens somewhere between the atom and the cat.
So no actual zombie cats in Copenhagen view.
Definitely no actual zombie cats. So the weirdness is contained at the microscopic level, or within the mathematical formalism used for prediction.
And even Schrödinger himself later on seemed to view the maths more as a tool.
It seems that way. The essay quotes him reflecting later that the simple procedure of quantum mechanics might just be a very convenient calculational trick, a powerful trick, one that profoundly shaped our understanding, but maybe not the literal truth of reality itself.
Which brings us back to that fundamental choice, really.
It does. As the Aeon essay puts it, do you accept quantum mechanics as this incredibly successful but maybe symbolic framework for predicting probabilities? A tool?
Ooh.
Or do you believe, like Einstein and Schrödinger initially did, that it's incomplete, that there's a deeper, perhaps more intuitive theory of reality still out there waiting to be found? That's still a driving question in fundamental physics.
So what a journey from this technical critique Schrödinger made in a physics paper
Using this deliberately ridiculous case.
to this icon that shows up in movies, books, everywhere, sparking debates about reality itself.
It's become this incredibly potent symbol, hasn't it? Forcing us to grapple with observation, with chance, with the sheer strangeness of quantum mechanics and how it connects or doesn't to our world.
It really makes you think. So, considering all these angles, the superposition, many worlds, Copenhagen as a tool, what do you, listening now, think? What is the cat's state before the box opens?
And what does your answer tell you about how much we can really know? About the limits of our understanding? It's a question that, nearly a century on, still hasn't lost its power.
Absolutely. Well, if you